Now we will discuss the inner transition elements or F block elements. So this is the second part of the chapter D and F block elements. So D block elements we have discussed and the general properties. Now we shall discuss the F block or called as inner transition elements. So what are F block elements? The elements in which the additional electron enters in n-2f orbital, that is inner transition element. The valence shell configuration of these elements are n-2f 0 to 14, n-1d 0 to 1 and ns2. तो outer shell ns है, this is outer से पहले पेनल्टीमेट शेल और ये सेकेंड पेनल्टीमेट, मतलब उसके भी अंदर वाले शेल का f सब शेल फिल हो रहा है. The 4f transition metals, inner transition metals, are known as lanthanide because they come immediately after lanthanum. And 5f inner transition elements are called actinoids because they come after actinium. So we have two rows at the bottom of the periodic table. The two rows are lanthanides and actinoids. These are F block elements. The general electronic configuration of lanthanide and the ionic state and its configuration and atomic radii are given over here. So lanthanum atomic number 57 is a transition metal and you can see the configuration at 6s2 5d1. But after that cerium 58, it has electron in 4f1 6s2 and 5d1. Then praseodymium, it's 4f3 6s2. तो f d का एक इलेक्ट्रॉन f में शिफ्ट हो गया, so it's 4f3 and 6s2. ठीक है. Then neodymium has 4f3 6s2. Samarium 4f6 6s2. Now the important is यूरोपियम एंड गडोलियम. यूरोपियम और गडोलियम, देखो गडोलियम का तो नॉर्मल में हाफ फिल्ड था 4f7 6s2, बट यूरोपियम का हाफ फिल्ड हुआ क्योंकि डी का एक इलेक्ट्रॉन शिफ्ट हो गया. यहाँ पे 5d में एक इलेक्ट्रॉन है बट यहाँ पर नहीं है. तो यूरोपियम गडोलियम यू नीड टू लर्न द कॉन्फिगरेशन. Similarly, you need to learn the configuration for ytterbium and lutetium. Ytterbium, if you see, it has a configuration 4f14 6s2 and lutetium 4f14 6s2 and 5d1. तो यहाँ पे 5d इलेक्ट्रॉन इंटैक्ट है बट यहाँ पे 5d इलेक्ट्रॉन शिफ्ट होकर 4f में आ गया है. So that is where it starts for half filled and full filled configuration. Now we shall see the variation of atomic and ionic size. Now as the atomic number increases, each succeeding element contain one more electron in the 4f orbital. तो हर बार 4f में एक इलेक्ट्रॉन बढ़ता जाएगा and one proton in the nucleus. The 4f electron are ineffective in screening and the outer electron from the nucleus causes imperfect shielding. तो 4f में अगर इलेक्ट्रॉन ऐड भी हो रहे हैं बट न्यूक्लियस में हर बार चार्ज बढ़ रहा है, तो 4f के इलेक्ट्रॉन शील्ड बहुत पुअर शील्ड होते हैं, तो आउटर शेल इलेक्ट्रॉन पे फोर्स ज़्यादा एक्सपीरियंस होता है. As a result, there is a gradual decrease in the nucleus attraction for the outer electron. तो हर बार क्या हुआ, लेफ्ट टू राइट जा रहे हैं तो साइज डिक्रीज ही होता रहेगा क्योंकि न्यूक्लियर चार्ज 1 यूनिट से इंक्रीज हो रहा है, इलेक्ट्रॉन ऐड हो रहा है बट वो 4f में ऐड हो रहा है और 4f इलेक्ट्रॉन पुअर शील्ड की तरह एक्ट करते हैं. कॉन्सिक्वेंटली तो वो न्यूक्लियर चार्ज को रोक नहीं पाते और बाहर के इलेक्ट्रॉन पे लगता है जिसकी वजह से साइज छोटी हो जाती है. So consequently, the gradual decrease in size occur and this is called lanthanoid contraction. So left to right continuously the size decreases and this is lanthanoid contraction. Now what happens due to lanthanoid contraction? There is a close resemblance between 4d and 5d transition series. 5d के बाद fill होता है हमारा 4f ऑर्बिटल और यहाँ पर 4f ऑर्बिटल में जब पुअर शील्ड होते हैं तो इसके बाद जितने भी एलिमेंट्स आते हैं 5d सीरीज़ में उनका साइज़ छोटा है बिकॉज ऑफ लैंथेनाइड कंट्रैक्शन, इसलिए 4d और 5d के एलिमेंट्स का साइज सेम होता है. देन द आयनाइजेशन एंथैल्पी ऑफ 5d सीरीज इज हायर देन 3d एंड 4d बिकॉज इवन तो 5d में हम मानते शेल ज़्यादा है बट अंदर के इलेक्ट्रॉन पुअर शील्ड की तरह एक्ट करते हैं जिस वजह से आयनाइजेशन एंथैल्पी काफ़ी ज़्यादा होती है. Then it's very difficult to separate lanthanide because in nature they coexist together because of similar size और radii. तो lanthanide का similar size और radii होता है इसलिए वो नेचर में इकट्ठा मिलते हैं और उनको सेपरेट करना डिफ़िकल्ट है. Now ionization enthalpy, we have seen the size is decreasing, so they will have low ionization enthalpy as the electron is to be removed from S not from F. The first ionization enthalpy is 600 kilojoule per mole and second 1200, almost the double, and it is comparable with those of calcium. Due to low ionization enthalpy, lanthanide have an electropositive character and the normal oxidation state is +3. Now many lanthanides are colored because of F incompletely filled orbital. There is a possibility of an electron from F to jump into F orbital and this is called F to F transition. FF ट्रांजिशन की वजह से इलेक्ट्रॉन्स एक्साइट होते हैं और वो कलर एमिट करते हैं, दैट इज़ वाई दे आर कलर्ड. सेम लाइक डी ब्लॉक में अनपेड इलेक्ट्रॉन होते थे तो डी ट्रांजिशन था तो वहाँ पर भी कलर था, या FF ट्रांजिशन, दैट्स द डिफरेंस. द एब्जॉर्प्शन बैंड आर नैरो probably because of the excitation within F level. Lanthanum and lutetium do not show any color because lanthanum में ऑर्बिटल सारे वेकेंट है 4f और lutetium में सारे फुल्ली फिल्ड है, तो FF ट्रांजिशन दोनों में पॉसिबल नहीं है, so they don't show any kind of color. Next, magnetic property. Like D block, lanthanides also have ability to show paramagnetic because of unpaired electron or partly filled 4f orbital. So paramagnetism rises to maximum in neodymium and then pairing take place and paramagnetic character decreases. Lanthanides have very high magnetic susceptibilities due to their large number of unpaired F electrons. Definite सी बात है, F में 7 सबशेल है तो 7 unpaired electrons तो है और D में सिर्फ 5 ही possible थे. So they have more magnetic ability or magnetic susceptibility. Next, oxidation state. Now it's unlike D block. Unlike D block stating that D block have variable oxidation state, but lanthanoid have only +3 state as a stable state. So the +3 state in lanthanum, gadolinium, lutetium are especially stable, half filled, completely filled subshell. ठीक है, इसलिए वो stable है. Terbium and cerium are stable in +4 state as they attain noble gas configuration or half filled stability. Occasionally +2, +4 in solution or in solid state compound are also obtained. तो +3 के अलावा +2, +4 है, वो depend करता है stability electronic configuration. But even then, the irregularities arises due to the extra stability of empty, half-filled or full-filled F subshell. The most stable oxidation state of lanthanoid is +3. That is, the ions in +2 state tend to change to +3 by loss of electron, acting as a reducing agent. And those in +4 will gain electron and turn to +3 and they act as good oxidizing agent in aqueous solution. तो lanthanide normally +3 में stable है, तो अगर कोई +2 में होता है तो वो +3 में जाएगा by losing 1 electron and acting as reducing agent, और कोई +4 में है तो वो +3 में जाएगा by gaining electron acting as good oxidizing agent. Why Sm2+, samarium2+, europium2+ and ytterbium2+ in solution are good reducing agent? Because they readily lose electron to form trivalent as they are more stable in +3 state. But cerium4+ is a good oxidizing agent as it readily gains electron to convert to 3+. So it is the property that lanthanoids are more stable in +3 oxidation state. Now how do they appear? Physical properties. Lanthanides are silvery white soft metal and they tarnish readily in air. Hardness increases with increasing atomic number, samarium being steel hard. They are good conductor of heat and electricity. Promethium in 4F is highly radioactive. Now, chemical properties. These lanthanide combine with hydrogen gas. They combine with carbon to form carbide. They react with acid releasing hydrogen and form halides with halogen. They react with like water to form oxide and hydroxide, that is with oxygen and water they form oxide and hydroxide, and these hydroxides are basic in nature. So the chemical properties, if you see, they react with acid liberating hydrogen, they burn to form oxide, they burn with sulfur to form sulfide, with nitrogen to form nitride, carbon carbide, water hydroxide and halogen halide. तो Ln generally lanthanides के लिए होते हैं, तो वहाँ पर 4F fill होते हैं. Now we will discuss actinides. Here the radioactive elements are there in more amount. All isotopes are radioactive with only thorium, uranium 235, 238 and plutonium having long life. The thorium and uranium are naturally occurring and are more abundant in Earth's crust. The other are made by nuclear process. These elements in 5F orbitals जहाँ fill हो रहे हैं यानी कि actinoids में, these are called as transuranic elements because they are artificial elements. The dominant oxidation state of actinoid is +3. Actinoid also exhibit an oxidation state of +4. Some actinoids such as uranium, neptunium and plutonium have a state of +6. So actinoid have variable oxidation state. Actinide also show actinide contraction due to the poor shielding of nuclear charge by 5f electron. These actinoids are highly radioactive in nature and are man-made. So the size of atoms or M3 plus ion decreases along actinoid series, and this steady decrease in ionic or atomic radii with increase in atomic number is called actinoid contraction, and it is because of the poor shielding effect of 5f electron. And the electronic configuration is 5f 1 to 14, 6d 1 or 0, 7s 1 to 2. So these are the elements. They are paramagnetic in nature, but paramagnetic is more complex than that of lanthanide as they are highly radioactive. They have high melting and boiling point. They do not follow regular gradation of melting and boiling point with increase in atomic number because of the radioactive nature. We don't know the correct variation and it's highly complex. The ionization enthalpy is low and they are highly electropositive. These are also colored because they have unpaired electron in 5f. Again 5-5 transition can take place. बट जहाँ पे 5f 0 है, 5f में 7 है या 5f में 14 इलेक्ट्रॉन है, वो कलर शो नहीं करते क्योंकि वहाँ f2f ट्रांजिशन नहीं हो सकता. बट f की प्रॉपर्टीज़ 5f यानी कि एक्टिनॉइड की प्रॉपर्टीज ज़्यादा नहीं पता है. दे आर हाईली रेडियो एक्टिव और उनका स्ट्रक्चर बहुत ज़्यादा कॉम्प्लेक्स होता है. सो दिस इज अबाउट डी एंड एफ ब्लॉक एलिमेंट्स.